Have you ever gazed up at the night sky, marveling at the countless stars twinkling overhead, and wondered, where did all of this come from? What is the origin of the universe we inhabit? For centuries, humans have sought answers to these profound questions, crafting myths, stories, and theories that stretch the limits of imagination and understanding. Today, thanks to decades of scientific exploration, our best explanation is captured in a remarkable idea known as the Big Bang Theory. The Big Bang Theory stands as the leading scientific model for the origin and evolution of the universe. According to this theory, everything you see around you, all the galaxies, stars, planets, and even the very fabric of space and time, began about 13.8 billion years ago from an extraordinary event, unlike anything we can truly imagine. The universe did not begin as a gigantic explosion in a pre-existing space. Instead, it began as an unimaginably hot and dense point, often called a singularity, smaller than a single atom, containing all the matter, energy, and space that would ever exist. In the very first fraction of a second, the universe started to expand. But this wasn't an explosion throwing matter outward into empty space. Rather, space itself began stretching and growing, carrying all matter and energy with it. The temperature was staggering, trillions of degrees hotter than the core of any star. Matter, energy, space, and time were interwoven in ways nearly impossible to comprehend today. During these earliest moments, known as the Planck epoch, the laws of physics as we understand them break down. Gravity, electromagnetism, and the nuclear forces that hold atoms together may have behaved as a single, unified force. As the universe expanded, it cooled rapidly. Within the first second, familiar forces and fundamental particles began to take shape. Protons, neutrons, electrons, building blocks of all matter, came into existence within microseconds. In just the first few minutes, what scientists call Big Bang nucleosynthesis, the temperature had fallen enough for protons and neutrons to combine, forming the nuclei of the lightest elements. The vast majority of the universe became hydrogen and helium, with trace amounts of lithium and beryllium. The heavier elements, like carbon, oxygen, and iron, would come much later, forged in the hearts of stars. But the newborn universe remained a seething, opaque soup of particles and radiation. Photons, particles of light, could not travel freely. They bounced endlessly off free electrons, unable to move very far. It took about 380,000 years of cosmic expansion and cooling before a crucial event occurred: recombination. At this epoch, the temperature had dropped enough for electrons to combine with atomic nuclei, forming neutral atoms. For the first time, light could stream freely across the universe. That ancient glow is still with us today, though stretched into microwaves by billions of years of expansion. We call this relic the cosmic microwave background radiation, or CMB. The CMB is a faint afterglow, providing a direct snapshot of the infant universe, its temperature, structure, and composition imprinted across the heavens. It's like looking at a baby picture of the cosmos itself. What convinced scientists that the Big Bang Theory was correct? Let's explore the major lines of evidence. First, we observe that the universe is expanding. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery by examining the light from distant galaxies. He observed that galaxies are moving away from us, and the farther they are, the faster they recede. This is demonstrated by the redshift of their light, the stretching of light waves toward the red end of the spectrum, much like the sound of a siren drops in pitch as an ambulance drives away from you. This cosmic expansion suggests that the universe was smaller, hotter, and denser in the distant past. Second, the existence of the cosmic microwave background gives us a direct, observable window into the early universe. Discovered in 1965 by Arno Penzias and Robert Wilson, this faint microwave radiation fills the cosmos uniformly in every direction. Its detailed patterns, tiny hot and cold spots mapped by satellites like COBE, WMAP, and Planck, agree precisely with predictions from the Big Bang Theory. Third, scientists examined the abundance of light elements across the universe. The Big Bang Theory predicts exactly how much hydrogen, helium, and lithium should have formed in those first few minutes, and these predictions match the amounts we still observe in the oldest stars and interstellar gas clouds today. Lastly, in recent years, the discovery and measurement of primordial gravitational waves. The ripples in space-time predicted by Einstein's theory of general relativity has offered fresh and tantalizing support for the theory, though much remains to be explored in this realm. So, what happened after the first light? Over hundreds of millions of years, matter began to clump together under the influence of gravity, forming the first stars and galaxies. Within these stellar furnaces, heavier elements were forged through nuclear fusion, lighting up the cosmos and eventually sowing the seeds for planets, life, and complex structures. Supernova explosions scattered those elements far and wide, enriching the universe with the building blocks of everything we know. Our own solar system emerged from such recycled cosmic material about 4.6 billion years ago. The Earth itself is composed of atoms forged in ancient stars that lived and died long before our sun was born. In this way, every one of us is connected to the birth of the universe. As astronomer Carl Sagan once said, "We are made of star stuff." The atoms in your body were cooked in the hearts of long-extinct stars, bound together by the cosmic evolution set in motion by the Big Bang. But just as the theory answers many questions, it raises new ones. What, for example, sparked the Big Bang? Did something exist before, or did time itself begin in that primal moment? These are challenging questions, and current science does not yet provide definitive answers. Some theories suggest the universe underwent an even earlier era called cosmic inflation, a mind-bogglingly fast burst of expansion that smoothed out the cosmos and seeded the tiny fluctuations we now see in the CMB. Others speculate about the possibility of a multiverse, countless universes, each with its own properties, perhaps beyond our current ability to observe. And what about the future? The universe continues to expand, and that expansion is actually accelerating, driven by a mysterious phenomenon known as dark energy. What this means for the ultimate fate of the universe is still being debated. Will the cosmos expand forever, growing ever colder and emptier? Will it tear itself apart in a big rip, collapse in a big crunch, or end with a gentle fading into darkness? These remain open questions, driving forward new research and discovery. It's also important to note that the Big Bang Theory is not a story of chaos, explosion, or purely random events. Instead, it is a story of laws and patterns, of physics, chemistry, and geometry working together over immense scales of time and space, producing order and beauty from the simplest ingredients. Throughout human history, many ideas about the origin of the universe have come and gone. What sets the Big Bang Theory apart is its foundation in observational evidence and rigorous testing. Scientists continue to probe its predictions with ever more sophisticated telescopes, detectors, and experiments, refining our understanding with each new discovery. The journey to uncover our cosmic origins is far from over. Every year, new technologies give us sharper eyes with which to peer backward in time, capturing ancient light from galaxies formed when the universe was a mere fraction of its current age. Each observation brings fresh insight and, inevitably, more questions. So next time you step outside and look up at the stars, remember that you are witnessing a universe once compressed into a single tiny point. All the beauty and diversity you see, the arc of the Milky Way, the glow of distant galaxies, the vast cosmic web tying everything together, emerged from that singular moment, expanded and evolved over billions of years. The Big Bang Theory does not claim to know everything. It is a powerful framework to make sense of the data we gather, a model continually tested by observation and experiment. Where it falls short, curiosity drives the search for deeper answers. Mysteries like the nature of dark matter and dark energy, or the true origin of the Big Bang itself, remain open frontiers. In seeking these answers, we are participating in one of the greatest journeys of human discovery. Ultimately, the story of the Big Bang is not just about stars and galaxies, equations and telescopes. It's about the timeless drive to understand how everything started, how it evolved, and what it means to exist in a universe that is, quite literally, expanding before our eyes. With each discovery, picture, and theory, we come a little closer to unraveling the greatest questions ever asked. Where did everything come from? How did we get here? What is our place in the cosmos? The Big Bang Theory doesn't just explain the universe's beginning. It invites us to imagine its boundless possibilities, to remain ever curious about the ultimate nature of reality. The universe, from its smallest particles to its vastest structures, is a story still being written, a story we are privileged to witness and explore.